Um, this is going to be the third lesson in the geometry unit. Previous lesson was focused more on like sort of being able to talk about things in geometry, whereas this lesson you're going to actually feel like you're doing things for the most part, hopefully. With that said, let's look at what we're going to be interested in. We're going to have kind of a brief history on geometry because I've been meaning to stick that in somewhere. On just sort of the structure of what geometry is really all about. And then we're going to get into specifics with lengths and angles. Lengths of segments and measures of angles. So we begin with sort of this overview of, well, what is geometry? I don't think I've done this yet. And so I feel like I'm letting you down here a little bit without mentioning, well, what does the word geometry really even mean? It refers to earth measurement. Geo means earth. Words that include metry, like metric, for example, all refer to measurement. And so after basic counting, sort of humans started developing some basic geometry because there were all these practical applications in agriculture and construction. You could argue that geometry is the math that helped civilizations develop. And then with the Greeks, geometry took a more formal turn because the Greeks had the opportunity at the time, and it was something they were interested in. So where you first start seeing mathematicians and scientists in sort of the way that we mean it, people whose occupation it was to sit around and think. So this all kind of began with the philosophers that you might have heard of, like Socrates or Plato or Aristotle. And this was kind of an outgrowth of their philosophy, the idea that we got to have a very specific way of talking about what we're thinking about. And so we're going to kind of begin with the idea that, and I'm not going to have you write these down because in this class this is not the emphasis, but in the geometry class we talk a little more about these. I just kind of want you to have heard of them before you get to geometry. An axiom is something that you cannot really prove or disprove. It's sort of like obviously true. And you might also see these words, if you'd had somebody else for an algebra teacher, they sometimes refer to what I call the properties of algebra, like associative, commutative, identity, inverse, distributive. Some people refer to those as the axioms that sort of provide the foundation for algebra. If I were to be your geometry teacher, you would hear this word a lot, postulate. That's something you're going to accept to be true because the book said so, because I said so. Hopefully it makes sense. And it's just sort of to get you started. Whereas a theorem, not to be confused with a theory in science, is a statement that can be proven true using logical reasoning. So you're going to use some of these things you're assuming to be true, like definitions, axioms, postulates, or something you've already shown to be true in the past to sort of figure out new things. And that's sort of the basic structure of geometry. Well, where does this really kind of get its start? It goes back about 2,300 years ago. Euclid is often referred to as the father of geometry. He lived in Alexandria, Egypt, but he was not Egyptian in the sense that most you would think. He was an Alexandrian Greek. This was the time when the Greeks were dominant in the Mediterranean. He collected the works of other people, improved upon them, organized them into a book that we call the Elements. And it was basically a textbook. It was intended to teach other people the basics of what you and I call geometry. And scribes copied it over and over and over to preserve it for us to this day. It was one of the first books that was actually printed. It's one of the most printed books. It's gone through a lot of editions since the printing press was created about 500 years ago or so. To give you an idea of the importance of the elements, Abraham Lincoln, you might have heard of him, he's kind of a big deal, has a quote that goes something kind of like this: you never can make a lawyer if you do not understand Euclid. In other words, you would never be a successful lawyer if you can't follow geometric arguments as laid down by Euclid in his book Elements. Here are some of the axioms of Euclid. these are the things that are just very basic assumptions that Euclid knows he's using. Things which are equal to the same thing are also equal to one another. If equals be added to equals, the wholes are equal. If equals be subtracted from equals, the remainders are equal. Things which coincide with one another are equal to one another. The whole is greater than the part. Equal things can be divided into equal parts. Now, obviously Euclid didn't speak English, but I tried to phrase these in the way that Euclid would have in his texts so that you kind of get the flavor. And what I want to do with them is kind of show you real quick that if Euclid had had algebra, this would have been a lot easier. Things which are equal to the same thing are equal to one another. Well, that's basically our friend transitive property in disguise. If x is equal to y and z is equal to y, so here we have things that are equal to the same thing, well then they're equal to each other. X is equal to z. So he didn't have the name for it that we use, transitive property, but he was basically assuming the transitive property. If equals be added to equals, the wholes are equal. If equals be subtracted from equals, the remainders are equal. And let's see, equal things can be divided into equal parts. Those are basically the idea that if x is equal to y, then you can add the same thing on both sides. Or you can subtract the same thing on both sides. Or you can divide up x and y in the same way, like you cut each one in half, for example. They would be equal. So basically, 3 or 4 of these are what you and I would call like properties of algebra, that you can add, subtract, multiply, divide on both sides of an equation and it's still equal. Algebra really hadn't been invented yet, so he had these kind of like awkward wordings that are much easier expressed, in my opinion, using sort of symbols. Whole is greater than the part. It's just sort of that basic notion that if you take a whole rectangle and cut it into 2 parts, the original was more than, greater area than either of the pieces you get after cutting it up. Things which coincide with one another are equal to one another. It's kind of a cheesy example, but if you label this point A, this point B, and then you rename this point F and this point G, then the length from A to B is equal to the length from F to G, because those segments coincide. It's kind of a cheesy way of getting you to think about that, but it's kind of what coincide means. And then more famously, here are what are referred to as the 5 postulates of Euclidean geometry. And the first 4 are all pretty basic. They're going to be easy to agree to. You can connect 2 points to make a line. If you start with a segment, you can extend it into a line. If you have 2 points, you can use that to draw a circle by making one of the points the center and the other point the radius. If 2 things are right angles, then they have to be equal to each other. One thing that kind of messes people up with 4 is that they want to think about the measure of the angle being 90 degrees. And this is saying no matter how you measure the angle, if it's a right angle, the measures are the same. Because there's actually other ways to measure angles besides degrees. Alright. The 5th one's where it gets a little tricky. It just seems a lot more complicated. In fact, Euclid wasn't satisfied with it himself, and for hundreds and hundreds of years, mathematicians tried to clean this up. In fact, this isn't even Euclid's original version. This is sort of a cleaned up version that I prefer. Given a line and a point not on the line, there is exactly one line that can be drawn through the point that does not intersect the line. A sort of an easier way of saying that is that if you have a line L and a point P not on L, then you are guaranteed the existence of exactly one. Ooh, I missed pretty badly actually. You're guaranteed the existence of. Wow, still missed. Exactly one line call it, forgot to label it, call it M, that goes through point P and never intersects L. In other words, the fifth is often referred to as the parallel postulate, because it's the idea that parallel lines exist because we say so, basically. And it turns out that's a really big problem, that if you don't assume parallel lines exist, you will actually end up creating different forms of geometry. It's what mathematicians finally figured out a few hundred years ago, but that's a story for a different time and place. Now to get into kind of what we really want to get into. So there wasn't a lot there to kind of write down. Most of that was just to kind of get your mind in this, sort of the setting of, okay, we care about geometry, we're measuring things, realize that a lot of this is going to be assumptions. So our first big assumption is in a geometry class referred to as the ruler postulate. We already talked about this earlier in the year when we were talking about the number line. It's just the idea of how to do distance on the number line is how far apart are 3 and 7? 4. That's the basic idea here. 7 minus 3 is 4. The absolute value is necessary in case you do the subtraction in the wrong order, so to speak. What I really want to start with in terms of things you actually probably need to write down is congruent is an idea that some of you might have forgotten from middle school math, and so we'll start with congruent segments, and we'll do congruent angles a little bit later. Segments that have the same length are called congruent, and the point of emphasis here is that the lengths are equal. So QR equals ST would say that this length from there to there is equal to that length from there to there. Excuse me. Whereas the segments themselves, the actual mental objects we think of, are said to be congruent, and our symbol for congruent is like an equal sign with a wave or the tilde above it. So let's take a word you probably already kind of know and redefine it using the idea of congruent. The midpoint of a segment from A to B is the point M between A and B such that AM, the segment, is congruent to the segment MB, or it divides the lengths into 2 equal parts. I don't think you need to write that down, but I was just trying to get you to think about the idea of, is that an easier way to talk about midpoints? In fact, I think a lot of you probably don't have a very exact way of talking about midpoints if you actually stopped and thought about it. Okay, this is a big idea. Segment addition postulate. If point Q is between points P and R, then the distance PR is equal to the distance PQ plus QR. If you have a line or a line segment and point Q is between P and R on that line, then the lengths are additive. You can take from P to Q, add it to Q to R, and it's the same as the length from P to R. One way to think of this is that when you have like a length of string and you cut it into 2 pieces, the total length of the pieces is equal to the original length of the string. We're going to assume, it's a postulate, so we're just going to kind of assume it's true. We're going to assume that when you cut lengths up, you don't lose any length, basically. We won't really use the backwards version of this, so to speak. For those of you that have paid good attention in the logic and reasoning, this would be like sort of the converse of this statement. If it's true that the lengths work out this way, then the points are going to be collinear with Q in between P and R. Big idea here, I think what honestly most of you need to do for your notes is sort of sketch a diagram similar to this and write this statement down. How do we use this? Well, some of you have already probably done the problems on Alex like this, but in your notes you have an example that looks kind of like this. And it says, okay, you've got a picture, you're given 3 of the lengths, you need to find 3 of the lengths. Well, how could you get started? I would start by kind of labeling my lengths as best I can. So I know that from there to there, A to D is 20. And I know that A to B is 15. And I know that C to D is 13. There's more than one way to do this. By the way, what we're going to do is kind of do segment addition, but in reverse. We're going to think it's more like a segment subtraction, but the point is that the idea works. Well, B to D, you could think of, well, I know what it is from A to D. I know what it is from A to B. I want B to D. I want this little length right here. So I know that AD is AB plus BD. I know that AD is 20. I know AB is 15. And most of you are already ahead of me. You see how this is kind of related to equation solving. Subtract that length over. B to D has to be 5. And it's 5 units. We don't know whether it's inches, meters, yards, miles. The point is, a lot of these problems are unitless. If that length's 20 and that length's 15, then that length would have to be 5. That's the difference between them. And it's all dependent on the way the diagram looks, or the relationships. And you can kind of figure out these other ones in a similar fashion. I'm going to go ahead and write in that this is 5. A to C, that's 20. That's 13. So AC, I'm going to find that by doing, like, basically what I end up doing is 20 minus 13. So this is 7 from A to C. And then there's a couple different ways to find from C to B. You know the whole thing's 20. You know that that's part 7. You know that that part's 5. That's 12 altogether. So this chunk in the middle would have to be 8. A different way to do that is you could say, well, that's 15, that's 13, that's 28. But I've counted this part twice. So how much more than 20 is it? Well, it's 8 more. So the parts I've counted twice would have to be 8. There's a couple different ways to kind of go about reasoning your way through this. Don't think that the way I do it is the only way. And then we have on the notes kind of a more complicated example where there's not even a picture. It just says, suppose point K is between points J and L. Gives you some information. Solve for X. Give each segment length. And so hopefully you're not too terribly shocked that if you don't have a picture to begin with, you should probably draw one. It doesn't. So how do we draw them? Well, K is between J and L. So if that's J and that's L, I don't know where K is, but I'm going to put it between J and L. And then by segment addition, we would have that JK plus KL would have to equal JL. But we were told kind of in the prompt of the problem what each of these things were. JK is 2x plus 15. I'm going to put parentheses around that. They're not necessary. It's just to emphasize that all that used to be JK. KL is 3x minus 7. And then JL is 6x plus 1. And again, a lot of you have already kind of caught on how this is like equation solving. We just need to combine like terms to get started here. It would be 5x plus 8 is 6x plus 1. Well, if we subtract 5x, 8 is x plus 1. So x is going to have to be 7. But going back to the directions, we weren't just solving for x, we were also finding all these lengths. So we go up here real quick. Let's start with this one. 2 times 7 is 14. 14 plus 15 is 29. 3 times 7 is 21. 21 minus 7 is 14. 6 times 7 is 42 plus 1 makes, 43. And then you could check and say, well, it's 29 plus 14, 43 like it's supposed to be, and it is. So that's a way to know you're right on this problem. You could say, well, just add the numbers and make sure it adds up to 43 like it's supposed to, and it does. Alright, so the rest of this lesson is about angles. And we haven't really talked about angles yet this year. We talked about segments a little bit in a previous geometry lesson. So we're going to talk a lot about angles. And I'm just making sure you know this stuff in the way that you're supposed to. Do not write a bunch of this down under angle on your sheet. Just write down the very basic part. So let's start with just what is an angle. An angle is a geometric figure consisting of two rays with a common endpoint. Alright? And so a lot of you, for your definition of angle, everybody knows that's what an angle looks like. So just think about, well, what is this thing really? It's two rays that are beginning at the same point. They have the same endpoint. Well, a lot of you are probably used to calling those rays the sides of the angle. The endpoint is the vertex. The angle kind of comes down and makes a V for vertex, so that's the vertex. When I teach geometry, one of the mistakes I see a lot at the beginning of the year is people have trouble naming angles. Realize that in this picture there are actually three correct ways to name this angle. Angle BAC, angle CAB. The order of these here does not matter as long as A is in the middle, because the middle is the vertex. Or you can name it by just the vertex as A. So here's angle A. Sometimes you'll also see like a little 1 right here, and you would call that angle 1. Or you could see a Greek alpha, and that would be angle alpha. So sometimes you see Greek letters or numbers. That was supposed to be an alpha, and it kind of printed out funny. So just ignore that symbol. I will not name an angle using that symbol. More about angles. Again, I don't think you have to write this down. Interior and exterior. Most of you know that those are fancy words for inside and outside. I bet everybody in here can look at the picture and agree that, the red points are outside the angle, the blue points are inside the angle. An easy way to decide is that idea that if you connect the sides of the angle with a segment, that's the interior of the angle. So that's kind of what this picture is about. You've got this blue point's definitely in the interior because you connect these 2 points that are on the sides of the angle. It goes through that point. Again, I don't think you have to write any of that down or draw that picture. I just want to make sure you understand angles as well as you can. Adjacent in everyday life means next to. So what's it mean for two angles to be next to each other? Well, most of you know that it's that picture. But what's going on in that picture is you have two angles that have a common endpoint, a common side, and no common interior points. And in a situation like this, you have to use the 3 points to name the angle. You can't get sloppy and say angle A, because there's 3 different angles in that picture that all have vertex A. So just kind of avoid that. Alright, so the next thing that I really actually want you to write down is the definition of circle. And some of you might be like, well, how do we just jump from circle to angle? I promise there's a reason. So what is a circle? A circle is the set of points in the plane that are this distance called the radius from this point called the center. And you could also, a lot of you maybe think of a circle as a full revolution or rotation. The idea of a circle is kind of like when you spin something, it goes in a circle. The reason why we have to talk about circles is most of you, probably as soon as I started talking about angles, want to start talking about degrees. And technically, a degree is a unit of measure that is, by definition, one part out of 360 of a full circle. And so it's kind of backwards to talk about degrees until you've talked about circles. And so that's why I had to go ahead and, in my opinion, include a little bit here about circles real quick. And most people think about it backwards with the 360 degrees in a circle thing. You know, realize that that's a definition that ancient Babylonians came up with thousands and thousands of years ago. They intentionally divided the circle into 360 parts and made that a degree. That was how it got started. And just kind of think about this for a second. This is more, again, something you're just thinking about. So we've created a ruler in the past using the number line. So how do we create a protractor? Well, there are infinitely many points along the circle. There are infinitely many numbers between 0 and 360, which is the degrees in the circle. So what we do is we create, just like we did the number line, we create a relationship to where every point on the circle is paired up with some number between 0 and 360, and we call that number the measure of the angle. And so what would you do to do that? Well, you cheat and you call point A is both 0 and 360. B on the opposite end of the diameter is 180. And then in that picture, C would be, about 45 degrees or so, because if you start pairing up all the points, C is going to get paired with some number. And again, I think based on just the way it looks to be roughly in the neighborhood of 45, whereas a point right in here might get paired with like 170, or a point right here gets paired with 270, or a point right here gets paired with, say, 300. And so that's kind of the idea of how you measure angles. You just pair up the points on a circle with numbers between 0 and 360 because you defined that there are 360 degrees in a circle. So there you go. There's kind of the idea. That's the kind of a fairly standard protractor image. So congruent angles have the same measure, just like congruent segments have the same measure. We talk about measure of an angle has this little m in front of it, whereas the angles themselves are congruent. So don't get confused by that. That's a kind of, again, a big deal in geometry. When I first few weeks of the year, a lot of students have trouble with that. So I'm trying to give you a head start on that. And again, those of you that are already in geometry, this is just a review for you. Bisect, most of you aren't shocked. That means cut into two. And so just like a midpoint would cut a segment in half, an angle bisector is a ray that's going to cut an angle in half or into two equal parts. We're not going to do a lot with that, but I wasn't sure if it might come up on Alex or not, so I thought I'd go ahead and put it on there. And you can almost ignore the words here. It's that same idea with segment addition, that you can cut angles up and not lose any part of their measure, or that you can put angles together to get the whole angle. That's really what we're wanting here. So for this angle addition postulate, I already put the picture on there. Most of you, I'm really just wanting you to write this next to that picture, because these words, it's true. It's the accurate description of what's going on here, but most of you just understand the algebra version so much better. Classifying angles, most of you know this already, at least for acute, right, and obtuse, probably even straight. Through and reflex in case you're curious. Acute angles are between 0 and 90 degrees. A right angle is exactly 90 degrees. An obtuse angle is between 90 and 180. A straight angle is exactly 180 degrees, and in case you didn't know it, an angle greater than 180 but less than 360 is a reflex angle. Most of us are used to going the short way around here, which, would still be an obtuse angle in this case. But if you kind of go the long way around and get a measure that's greater than 180, that's technically a reflex angle. You don't hear that a lot, but just in case you do. That leaves us with one last example here real quick. We've got this picture. It says solve for x. Find the measure of each angle in the circle. Let's see. Let's label the thread here. So the angle AOB, this angle right here, is 8x. BOD is 10x minus 22. COD is 6x minus 2. And angle AOC is 4x plus 6. And again, please realize here what I'm doing is I'm labeling the angles, measure. Well, thanks to angle addition and the idea that a circle's 360, I can get started on this problem by saying that if you add up all these measures, that you'd better get 360 degrees. And again, that's just angle addition and the definition or the idea of a circle. I know that if I add those four angles up, I'll get 360 degrees. But the problem gives me in the prompt that one's 8x, that one's 10x minus 22, again, the parentheses are just to emphasize that used to be an angle measure. 6x minus 2, and then angle AOC was 4x plus 6. That should be 360. Okay, well now I'm just combining like terms like crazy. 8x, 10x is 18x. 6 more x's would make 24x. 4 more make 28x. Minus 24 plus 6 would be minus 18 is 360. Just solving the equation now, we would add 18. 28x is 378. And if you divide by 28, and I didn't just do this in my head, I'm looking at my scratch work where I did it before I started filming, you get 13.5. So that's x, and then we could go through and put in x for each of these to get the angle measure. And this video is already over 30 minutes, so I'm not going to sit there and walk you through that work. I'm just going to promise you that you should get 108 for that angle, 113 for that angle, 79 degrees for angle COD, and 60 degrees for angle AOC. I encourage you to check my work and make sure those add up to 360 degrees. I hope this has helped you kind of review and preview some basic geometry you're kind of expected to know, but helped you maybe solve some problems you didn't know how to solve before. So thank you, and I'll see you next time.